11%, and then the other sectors are typically, many quite low, around 1 to 3% is what we are seeing. So this kind of tells you that transport is a pretty big source in Indore in terms of the emissions, both exhaust as well as this resuspended road dust. Likewise, for PM10, you're looking at, we estimate about 13,500 metric tons per year. Again, together, transport, road dust and transport vehicle exhaust and the non-exhaust emissions, you have about 81% of the PM10 emissions is coming from the transport sector. And then of course the other sources, industries and household, each about 7%, and the remaining source sectors. So you can kind of see that both PM10 and PM2.5, you have a pretty big contribution from transport sources, and road dust is a significant component. So if you really want to control these emissions, then you really need to also tackle the road dust component. So when we then distribute these emissions spatially, you can kind of see this is how these emissions are desegregated spatially on a 1 kilometer grid for both PM2.5 and PM10. So there are definitely some hotspots central of the city. The northern part, that's an industrial area. So you kind of see these hotspots where these emissions are high. So I mentioned about the site identification process, that it's a structured process. So we have these, general guidelines that are there, that's published by the Pollution Control Board as well as other organizations across the world in terms of where you should monitor and kind of picking the site. But then depending, in order to kind of get to that level, then you need to go through a series of steps. And so we kind of the team developed kind of a structured process to identify these sites for monitoring, or to set up these air quality monitors depending on the site or the objective of these sites. So the goal was to use these, of course, now we have this emissions inventory data, and then we also have the secondary data. Using that, and identify different station types, let's say the residential or urban site, background site. So the overall approach is first identify these wards based on these emission inventories and activity data that we have. Then identify a suitable location that meets the CPCB criteria. So this identifying these wards and the suitable location is what this approach gets us to, and then after that, then you follow the CPCB criteria to deploy the instruments and have that site operational. So this approach is scalable and adoptable by the local bodies. So in terms of the selection itself, so this is the kind of the process that was followed to select the sites. So one is identifying through literature review, identifying these the different air pollution sources through our activity data collection that we did, as well as the emission inventories, and through all these additional information where that tells us the land use type, the socioeconomic status, the land cover information, the number of households. So it kind of lists all these different parameters factors that we looked at. And then we go through this stepwise process for selecting the wards. And so that's done using that, the list of steps at the bottom left that talks about first identifying this, how dense is in terms of the pollution source itself, the activity itself in that ward. Then coming up with a methodology to come up with the cumulative score depending on the different source categories that are there, and the density and the activity information of that. And then based on the objective of the site, whether you want nearly equal contribution of all sites, of all sources, or do you want a site that is specifically needs to be representative of, say, residential, needs to be representative of near road conditions needs to be representative of industrial sector. So accordingly, then you decide which ones to take. So this is a key step that kind of tells allows coming up with a number based approach to be able to pick the wards that we can then further identify suitable locations within that ward. Once this method was developed, then the wards were identified. Then the team also did some validation of this process to see if these sites selected are representative in terms of, based on kind of work from the literature, in terms of the impacts that's been seen before, the hotspots that's been identified before. So where do we see those in the same areas where we find these, where we've identified these sites. So based on that, then we came up with these different sites, the background site, peri-urban site, the representative source representative site, as well as a site that is kind of representative of all sources, somewhat equal contributions. So these are all the different factors that all went into this. So obviously for transportation, these are all the parameters that were looked at in terms of the possible sources and the associated activities that were looked at when trying to come up with these scoring mechanisms. So this is an example of kind of the final output that we get out of this process. So the graph on the right kind of shows the different scores for each of those wards. So the x-axis is the different wards referred to by ward number, and the y-axis, it kind of shows the contribution of relative contribution of each source to that overall normalized score. And so the team is in the process of submitting this to a journal article. So this information will be available for anyone to look at further and expand more in terms of trying to kind of replicate this approach for other locations. So you can see some locations you have, say, for example, if you're looking at ward 49, you can see that the orange color, which is cooking, has a higher contribution. So if you're looking for a site that needs to be representative of, say, household cooking, then that would be the one that you pick. But if you're looking for an urban site that has somewhat similar influence, then you kind of look at the ward where you have nearly equal contribution of all of these colors. So that is how we did this, and came up with this the list of wards for the different site categories. And this kind of tells the wards that were recommended for the monitoring sites. And based on that, then we finally also chose we also looked at these wind patterns to understand where the wind is coming from during both, during the different seasons. So you can also then identify the background sites for monitoring. So based on that, we came up with these 5 sites with the different objectives. The first one is it's at a government school in Malav Kanya. We refer to it as Malav Kanya site, and it's an urban site with the nearly equal influence from all sources based on the approach that we've developed. So based on the emissions, based on the activity data, based on wind patterns. So that is what we assess to be that site to be a representative site for all source contributions. Then the site at the public health office at Musakedi, that's a low-income residential site. Then there's a site at Bijalpur, representative of traffic, site at Sanvar Road, which is at the industrial cluster in the northern part of Indore, and then the Bicholi Hapsi government school as a background or peri-urban site. So these are this is how we came up with these different sites, and at each of these sites, this table kind of shows what type of monitoring we did. So as part of this Clean Air Catalyst project, one of the unique things that we did is also establishing regulatory grade monitoring at 3 locations. So one is continuous ambient air quality monitoring station itself, the CAQMS, where we are currently monitoring PM 2.5 and carbon monoxide using a reference, regulatory grade instrument, and black carbon using research grade instrument. Then we have PM 2.5 at the Musakedi site and the Bicholi Hapsi site. So we are doing this regulatory monitoring at these three sites. So the urban site alone has these three parameters: PM 2.5, black carbon, and carbon monoxide. For source apportionment, we did winter and summer monitoring for both PM 2.5 and PM 10 at all these 5 locations. So that is just seasonal sampling for PM 2.5, PM 10 at all these 5 locations. In addition to that, we also did a year-long sampling just for PM 2.5 at the urban site. So that will also then help us to kind of look at this beyond just these 2 seasons. What's the source contribution across the whole year? So we had samples also collected. That is just for PM 2.5. This kind of shows the different locations of these sites. So the industrial site is in the north, then obviously the urban site is near the center part. The Bicholi Hapsi, the peri-urban site, is on the east, the right side. The southernmost site is representative of traffic, and then the low income site is to the southeast of Indore. This I just mentioned. So the urban site is that site that representative of all these different source categories. And then, of course, the low-income residential, mostly vehicular and household emissions. And the peri-urban site, supposedly for background as well as, but you have, suppose it's at the, kind of rural peri-urban nature, you also have this open biomass burning influence. So the source apportionment work is in progress, but what's listed here is just this gravimetric mass for both PM 2.5 and PM 10 for both of these seasons across across these five sites. So few things that you can obviously see that the concentrations are much higher during winter season as opposed to summer season, and and then the industrial site obviously has the highest concentration among these 5 sites that we look at. Interestingly enough, the background site or the peri-urban site also has high PM 2.5 and high PM 2.10 emissions during winter. And I think that we've kind of noticed that site has this waste burning, the biomass combustion that's happening. So that also adds to the observed concentrations. So just based on this, then some of the insights that you can gain just from the mass data is the fraction of PM 2.5 and in PM 10, it's on average higher during winter. So during winter, about 41% of PM 10 is is in the fine particle range, while during summer it's only 26%. So during summer you have a larger fraction of the coarse size particles, i.e. PM 10 minus PM 2.5. But during winter you have a higher fraction of this. It's still less than 50%, but definitely relatively larger than what you observe in summer. And the PM 2.5 concentrations during winter are also twice that what you see during summer period. So just based on just this information itself, even while we wait this chemical speciation data to come in, you can kind of, basically come up with a hypothesis that during winter, with nearly 41% being in the fine particle range, so you can see that you have a higher concentration of a higher contribution of combustion sources during winter as opposed to summer, and also secondary aerosols that are there during winter season. Because that's what usually end up in the PM 2.5. Mostly it's combustion oriented sources and secondary formation that you see. The preliminary data that we've seen in terms of the chemical speciation data It also indicates higher concentrations of black carbon, organic carbon, and secondary inorganic aerosols, sulfate, nitrate, ammonium, potassium. Potassium is primary, but second, sulfate, nitrate, and ammonium. So basically that, just the last 2 points kind of align with what we were hypothesizing, that obviously there's a lot higher contribution of combustion sources and secondary aerosols during winter season. So that is just based on this gravimetric mass. Now, we also mentioned about this continuous, the air quality monitoring that is happening. Like I said, it's the three sites. One side, the urban site, has PM2.5, CO, and black carbon, and then PM2.5 at the other two sites. So this is the continuous ambient air quality monitoring station that's at the urban site. So it has the PM2.5, CO, and both of those reference grade, and then this auto calibrator for the CO measurements. There's a zero edge generator also, and then you have this black carbon that's kind of behind this computer screen there, that is also mounted there. That is a research grade instrument. And then the PM 2.5 BAMS beta attenuation monitor at the other two sites, the Musakedi, the low income residential, and the peri-urban sites. So just a preliminary analysis of the data itself. So when you look at these different seasons, it's winter and then the pre-monsoon. That is what is referred as, it will be referred to it as a summer in the source apportionment graphs. But anyway, the winter, pre-monsoon, and then you have the monsoon, post-monsoon. But basically, you kind of see higher concentrations during the winter period and the post-monsoon. So effectively from October through about Jan-Feb time period, you have really high concentrations. And then of course this monsoon period and the pre-monsoon period, then you have lower concentrations. And likewise, CO also, you're seeing higher concentrations during the post-monsoon and the winter season. On the right, we have this black carbon data that is from that instrument. I think the important thing to kind of note here is that the black carbon is about 15-18% of the PM 2.5 during the winter season. And during other seasons, it's I think monsoon season is about, so the other seasons is about anywhere from 7 to 10%. So this is the relative fraction of black carbon to PM 2.5 is it's quite high. When you look at other countries, say in the West, the concentrations are typically less than I think around 5 to 7% is what we typically see, and that too during polluted periods. So this is definitely kind of high in terms of the contribution of BC to PM 2.5. And based on the analysis, we also see that the PM 2.5 exceeded the standard about 80% of the days during these high episode period, both the post-monsoon and the winter period. And this is an example of the diurnal variation that we are seeing. So basically, how do the concentrations vary over time during the day for these across these different sites and during different seasons. I think the key thing to note is you kind of see this bimodal pattern during the winter and the the post monsoon seasons, and not so much for the monsoon season. Obviously, that's where the concentrations get reduced because of rain. But these during winter and the post monsoon, then you have kind of see this impact of emissions that's showing up in these bimodal diurnal variation. That is for PM 2.5. On this kind of shows the same thing for CO, carbon monoxide, and black carbon. It's interesting when you look at it. See, for PM 2.5, the concentrations, the x-axis is time, right? So somewhere during the daytime, the afternoon time periods, you actually see a dip in the concentrations for PM 2.5 pretty much across most of these sites during the winter post monsoon. But when you look at the black carbon data during winter season, you pretty much see almost the concentrations remain high throughout the day, and kind of suggesting kind of continuous activity of nearby emission sources, mostly we attribute to kind of burning. So that is kind of happening. You can see that impact in winter, particularly, that is quite obvious compared to these other seasons. And with CO, you obviously see this peak at night time during the vehicle rush hour period. And when you look at the spatial correlations across these different sites, PM 2.5 exhibits high correlation across these three sites that we have, just indicating that obviously it's a well mixed signal. It's regional nature of this PM 2.5. And when we look at the same data, combining it with the meteorological data, in other words, if you do these pollution roses, it also kind of gives some insights as to the conditions when the concentration is high and at which, eh, yeah, conditions where this concentration is high, the direction from which this pollution is might be coming. So that's an interesting way to look at it. So if you look at, let's say the urban side, you kind of see the red dot at the center. These concentric circles are the wind speeds, the different wind speeds. Uh, and so you can clearly see that at the very center where it's very low wind speeds, nearly idle conditions, you see the high concentrations are quite high. uh, and so that kind of also indicates that it's kind of, you see this more of this local influence at that the emissions that are trapped under this low wind speed conditions. uh, and same thing, similar type of pattern that you see for this low income residential site. But for the peri-urban site, you kind of see that obviously you see this red, the high concentrations at the center, but you're also able to see a little bit of the concentration distribution in the east. So kind of saying that there's this influence from both the non-local sources also that you are seeing at these at this peri-urban site. So basically indicating the impact of the long range transport from other regions. So it's an interesting way to look at it and also kind of get an understanding of whether it's a local source or some indicative understanding of whether it's local or non-local. In terms of the black carbon itself, just a little bit about what type of instrument it is. It's a micro earth instrument, so it's a portable instrument. It has uses. It's a light absorption based instrument. It measures at it's a 5 wavelength instrument, and obviously the measurement at 880 nanometers is taken as the black carbon concentration. But then this wavelength, the multi-wavelength nature of the instrument also allows you to look at the dependence of this light absorption on the wavelength of the light. Uh, so that's basically the absorption angstrom exponent, and that's been used in literature. Depending on that value, you can so estimated to be indicative of either fresh emission sources with either black carbon or brown carbon. So trying to kind of get an understanding of this dependence of wavelength dependence of this absorption kind of also sheds insight into that. And several studies in the literature have also used this approach to delineate between fossil fuel versus biomass combustion. And so that is an interesting aspect for us as we try to further take this black carbon data to use this 5 wavelength data to then look at the relative contribution of these two, fossil fuel versus biomass, to help for shed further insights into this black carbon. kind of augmenting what we find, what our findings will be from this receptor modeling effort. So I think that's an interesting thing that we are hoping to have soon. So the same, some scientific interferences, which I think I've already kind of mentioned, during the talk here. Basically, yes, winter and post-monsoon, there's also this non-local signal at the peri-urban site. And there's obviously this rainfall having an impact on scavenging. In addition to this, we are also doing this regional chemical transport modeling. That's I mentioned this. Catalyst is a partnership across various organizations. So this regional chemical transport modeling is done by a consortium called MapAQ. So they are doing this air quality modeling for us. So that's using this WRF-Chem model, weather research and forecast with chemistry. That model is being run to model the baseline concentrations and in Indore and surrounding regions. And we're using CO as a tracer for sources within and outside Indore. Doing that for an entire year. And so we hope that this simulation, once the results are available, then it will help us complement any findings that we find from the receptor modeling and provide a more, I think the utility of this type of modeling is you are able to kind of see the spatial understanding of the concentration distribution, predicted concentration distribution within and outside Indore. So far I've talked about the different components that went into that first pillar of the strategy. That's the source awareness. So all of this kind of help us to understand what the sources are, what is the relative contribution, what's the dominant source sector, and how does it vary over the period of a day, month, season. So all that information we were able to gather based on the process. And then the next one, that's the pillar, was kind of identifying these effective solutions. So that also we went through kind of a very detailed process of identifying these solutions. So kind of getting to the root cause, performing root cause analysis itself of what would be causing this, the emissions for different source sectors, developing a very long list of potential solutions, and then kind of shortlisting it for the most feasible and desirable solutions. And then we developed these scenarios for impact. So it was kind of a quite long process, or a structured process that we went through to identify these the effective solutions that could be utilized. And so, because given that the transport sector has contributes to about 70% of PM2.5 emissions, including this road dust, resurfactant road dust, and 81% of PM10. So we developed a detailed suite of measures for transportation sector for Indore. And so it consists of these 8 solutions that we list here. Includes anywhere from kind of scrapping old vehicles, retrofitting the old diesel vehicles with diesel particulate filters, encouraging more of the shift from private transport to public transport, encouraging non-motorized transport, that is using just walking and using bicycles, adding more parking regulations, so it kind of helps remove congestions on streets where you have street parking, on-street parking, restricting the heavy commercial vehicles, say restriction during peak hours, so they also do minimize this congestion that might happen during peak hours. And then to add to all of that, obviously you need this road dust mitigation, because that is a significant component, like you saw in these emission inventory. So without that, the other efforts are really not going to be that effective. So that road dust mitigation has to be a component of any of these that we choose. And then finally, the PUC, pollution under control checks. So if the city were to implement all of these measures as a combined suite of measures, then we estimate about 26% of reduction in PM2.5 emissions and nearly 20% of reduction in PM10 emissions. So that is what we estimate based on the the changes in the activity, and obviously based on the the approach for all of these different solutions. Once it's all implemented as a, all of these 8 solutions are implemented, then this is how much we anticipate that we'll be able to see in terms of the emission reduction itself. And I mentioned it's one of the primary goal, I think, as part of this whole solution bucket, is to be able to encourage this mode shift from private transport to public transport, and and so some of these measures that you can then test out, and as part of this effort, we as part of these low emission zones, and so we highlight those measures from 3 to 7 are measures that are suitable for testing it out on as in a limited region as part of these low emission zones, and then maybe able to kind of scale it up. And finally, like I said, for any of this to be successful, you really need this partnership across, with different stakeholders. So this is kind of the last pillar of the strategy of this Clean Air Catalyst program, is to kind of create this coalition that will then help push this agenda forward, help push forward this implementation of these measures, and continue the conversation even after this project is over. So this coalition it consists of members from the different agencies, and it includes obviously representatives from the transport sector, but also other sectors as well. So because we want this coalition to be not just for the transport solutions, but all source sectors. So it has a broad representation from all the different agencies in Indore, as well as research institutions, the universities in Indore, the local universities there, as well as other organizations that will help push this agenda forward. This was launched in July of this year. Honorable Mayor of Indore launched this coalition, and we are now getting ready to move forward with some of these next steps using this coalition. So during that launch period, you can see there on the bottom right the different solutions that I just mentioned. So we also kind of got this feedback, inputs from the community itself, the coalition members, on the challenges that they see, what type of approaches one might take to do this, what are the factors that we need to consider when we really implement these solutions on the ground. So I think one thing forgot to mention earlier is that one of the unique nature of this Clean Air Catalyst is the co-creation process, meaning you develop these solutions for every step of this project. It was done in consultation with the relevant stakeholders. So it was you had this input from the stakeholder community, from the corporation, as well as the other organizations, the relevant organizations, on both in all these different steps. So it was a co-creation process altogether with participation and inputs, and so that was kind of a unique characteristics of this project. So I think that's where we are right now, and what we are currently working on next is being trying out some of these solutions. So on an experimental scale, testing them on ground in terms of the effectiveness of those solutions on the ground, and then developing. We've also developed a roadmap for kind of this implementation of this entire suite of measures that we have developed for the transportation sector. And also we are now kind of in that stage of doing this pilot scale testing, preparing for the pilot scale testing, at least for a few of those measures. So I think that kind of brings me to the end of this talk. I'll just say it's kind of just now going back to that, the initial schematic of the air quality management framework. So you kind of demonstrate this through this project. It kind of demonstrates the utility of the data sets, how the insights that we get from the gravimetric data, as well as and then confirmed by the chemical speciation data and the continuous air quality monitoring data, kind of then all builds the robust evidence to be able to then design effective solutions to take this forward. Yeah, so I think with that I'll end this. I just want to acknowledge USAID for funding this work. A similar effort is obviously being done in Nairobi and Indonesia as well as this Clean Catalyst is a big consortium of partners. So what I've shared here is just the work done by the team as a whole. And I just really want to acknowledge the inputs and contribution of every team member. So with that, I'll end, and yeah, happy to discuss further.
Thank you very much. Yeah, thank you very much, Prakash. It's a wonderful talk and giving wider informations about and implementing the tools, technologies, and also the ways that can be useful for addressing the air quality, particularly focused towards indoor. Any questions? So before I just thought because maybe I just like to know, that since you have worked both in developed countries, developing countries, some of the other Asian countries, so the air quality management is quite challenging from place to place. So do you have some things where we can learn from Western countries when we move towards East? That's where I'm trying to look at it. Several things has been already implemented. Now we are slowly catching up, and in that context, you would like to give some your thoughts.
Yeah.
Then you can just.
Yeah, thank you, Professor Nagendra, for that question. So yeah, so I think what I would say is that obviously each country has its own process. I think the main difference is that in the Western countries, it's they are far ahead in terms of obviously the formulation of the framework and the implementation of the solutions, and we are in the process of kind of catching up with that process. But I think the main difference is that the overall framework is well defined. There is a time bound nature, and there's an accountability aspect that is also there in the Western countries in terms of these, and it's a periodic effort as well. So they have this quality management. Every few years, every 5 years, you go and then revise these, assess whether these current standards are effective, and if not, revise it. So there is that process in place that's kind of well defined. I think India is also right now in that same path forward in terms of doing it. I think what would help us to kind of do, to leapfrog, is to identify solutions that are relevant for our conditions, and implement and scale it up quickly. I think, and then assess. I think what is currently missing, or I see as a gap at the moment, is being able to assess the effectiveness of those measures in terms of the whether the measures are yielding the benefits that they are intended to result in. So I think that is a gap I see in terms of where we need to probably work more on in trying to be able to identify come up with those estimates of those effectiveness, and then devise solutions accordingly. I think one aspect that would help with that effort in being able to identify the effectiveness is in my opinion also having this chemical speciation data on an year-round basis, at least at a few sites. The reason being so when you think about these measures, the control measures that are being implemented, it is phased in over time. You have these measures across different source sectors, and the implementation, it starts at a local scale and then you expand it spatially. So it's not like a switch that you turn on and off, right? It happens over a period of time. So the amount of the impact that you see on the measured concentrations, the ambient concentrations, is often quite small. And so really raising the question whether these measures are effective or not. And primarily because the scale is small, it's spatially localized, and it's phased in over time. The scale of implementation is also phased in over time. And to be able to then further look at that, I think the markers is what will help. Being able to track those markers over time will then help us answer the question of whether the measures that we are implementing are yielding the benefits that we are seeing. So whether this 5 microgram per cubic meter decrease that we are seeing, whether that would result, whether that is because of these measures. So I think being able to develop that type of methodology to assess those effectiveness of those measures is important to be able to understand. I think that I see as something that would help us, as we, particularly as India is right now implementing all this control measures in response to this NCAP, National Clean Air Program. It's important to do it right now, to have this baseline conditions as well as then periodically track it over time. I think the other challenge is also the nature is of the dispersed sources that we have. So I think that also adds to the challenge in terms of the coming up with relevant control technologies for such small dispersed sources that would then help be able to mitigate those emissions from those sources. So I think those two I see as kind of the major, maybe areas where we need to work further.
My other question is, maybe if you try to look at it in terms of the management aspects in developed countries, like there is not much emphasis on monitoring. I've seen that there are so many monitoring stations set up in developed countries, but many of the Asian countries, they're emphasizing on more monitoring stations. And for example, I try to look at it, how many focus sensors have been set up in any of the large developed cities, maybe compared to any other cities in South Asia. So is there any reason for these kind of things are influencing? I look at it more because this monitoring, again, it will produce a lot of data. Of course, there is always a knowledge gap, but knowledge gap is not that is so significant. It will influencing making a key policy decision. So why don't we get some leverage based on understanding, try to come up with implementing some policy so that we can more focus towards policy rather than again go back identifying the sources.
Sure.
And monitoring. What's your thoughts on that?
Yeah, no, so just for others, I think the question is about the need for air quality monitoring versus maybe focusing on solutions. So yeah, I mean, I think as far as India is concerned, obviously we have enough data and to show that we need to implement solutions, and we need to do that to reduce the ambient concentrations. So I think that is very clear. I think where this additional data would help, and it depends on what type of monitoring you're looking at. Could have multiple initiatives. It could help with tracking trends over time. It could help with public awareness, and of course this maybe on a local scale as well, kind of looking at from a personal exposure. But yeah, I agree. I think in terms of the ability to what we really need is to kind of move forward with implementation and scale up of the right set of solutions, and be able to assess the impact of those. So I think that is really important, because we need to be able to tell whether the measures that we are implementing are effective, and how effective those are, and if not, how do we optimize it, and how do we what type of strategy should we develop for doing that. So I think that is where the difference is. Yeah.
Any question from any of you? You have any question? You can wait for the chat.
There's a question in the chat on what measurable reductions in pollution levels can be expected to increase community engagement and behavioral changes resulting from any public awareness initiatives. So I think if I understand correctly, if the question is about what pollution level, what reduction can we expect to increase community engagement, behavioral change, I would actually switch the question the other way around, right? It's what type of behavioral change and community action is needed to result in a measurable reduction in pollution level. I think that is where it's important, because the public needs to come together to be able to we need to work collectively to reduce this impact of air pollution on all these different emission sources. So I think it's really important to kind of think of it from that angle, rather than saying what reduction can be expected to increase community engagement. So that is what I would recommend, kind of thinking from that angle. But I think that said, just in response, to the question itself, I don't know from what perspective the person is kind of asking this question, but basically, I think if you think of it in terms of the motivation for behavioral change or for community engagement, is when you see this appreciable change in the whatever metric you're looking at. So I think that is and that is going to be relative depending on where you look at. So I don't want to put a number or a criteria for that, but basically I think what it means is for there to be appreciable community engagement and behavioral change, I think the impact should be measurable. I think that is what is also a big challenge currently, is even though there are several measures that are being considered and implemented, again, like I said, the change that we are seeing is quite small, mainly because of the scale of implementation at the moment. So that will take time. So I think also there needs to be some awareness that is needed for the public also to understand that these efforts will take time, and then of course in parallel these efforts need to be scaled up and implemented quickly. So the next question is on what should be the measures we can follow, especially in transport, to improve the air pollution condition in other cities as well. Does population density play a critical role in urban planning? How to cope up with rapid urbanization? In speciation profile, we saw there is increase in BC compared to PM emission. What should be the reason, specifically in post monsoon? So I think there are like several questions included here, but if you kind of go by one, the measures we can follow specifically in transport to improve air pollution, and it also relates to this the next question about population density and urban planning. I think the key thing is the ability, the shift from private vehicles to public transport. So increasing that, enabling that mode shift to have a larger fraction of commuting by public transport will then help reduce the impact from the transportation sources. So I think that is probably one key aspect that all of us can help with in terms of being able to reduce the amount of private transport that we use, the amount and frequency of the private transport that we use, and increase the fraction of of the commuting that we use via public transport. So just increase that. I think that is where this urban planning obviously definitely has a big role in that, in terms of being able to properly plan the transit system, uh, and also kind of there's this looking at how to also enable this, what do they refer to as last mile connectivity. How do we enable that, so that then you can together enable this shift from private to public transport. The other question is on the increase in BC compared to PM. I think, yeah, that's what I think. What I mentioned is so specifically during this the post monsoon and winter season, we obviously see that increase in the black carbon concentrations. I mean, the PM also increases, but I think you're referring to that relative fraction of BC in PM. And like I said, I think that we anticipate that is as a result of this wood combustion that we see during the winter period for various purposes. Heating is one, but wood combustion we see as one of kind of the and biomass combustion that we see as one reason for that. We also see increased vehicular contributions also during that time period. So I think that's mainly what we are attributing it to at the moment, until we await these the source apportionment results. Any
Yeah, thank you very much, Prakash. I think it was a wonderful talk.
Thank you.
Yeah, on behalf of Department of Civil Engineering and Air Quality Management Association, and also the Indian International Conference, we would like to thank you for a wonderful talk, which very practical solution in addressing the air pollution problem. Thank you very much.
Thank you.
Maybe, I don't know whether you can all start your camera. We will have one picture with Dr. Prakash. So you can start your camera. We will just merge both the things together. So all others, maybe we can stand here, and we can also see somebody can take picture from that side. Okay, you can just, all of you can just stand. So all of you, can you start camera? Dheeraj is also watching. So come this side. We can take from that side, so that these people can also we can capture from that. So you can take it from that side. Come this side. All of you just be all taller can go back. Come, you can come. Yes, you may allow him to come. Yes, you will back here. Come here. Come here. Okay. Thank you. So just one more. Yeah, you can come. Yeah, Saket, you can. One of you can just take. Let him be there. Yeah. Thank you all for joining, and see you in the next air quality management lecture series. Thank you very much. Bye bye.